Welcome to EPG Pathshala in Computer Science. This is a series of lectures on computer networks. So we've been looking at quality of service in computer networks. So today we will be continuing with quality of service. We will look at one specific protocol that's used for quality of service, namely IntServ or integrated services. So we will start with different quality of service approaches, then we will look at IntServ in detail. So we'll also look at a protocol which is associated with IntServ, which is the Reservation protocol or RSVP protocol. So we will look at the details of these. So we have already been looking at different quality of service techniques. So the different quality of service techniques that we have are quality of service routing, admission control, signaling, classification, traffic shaping and policing, and scheduling. So what we have now got to look at is how the integrated services or whichever protocol we are talking about incorporates these various functionalities that are required for providing quality of service. So if you look at different approaches that have been used for supporting quality of service, you normally find there are two approaches. One is a fine-grained approach and the other is a coarse-grained approach. So in the fine-grained approach, what we do is that we provide quality of service to individual applications or individual flows. So which is why we call it as a fine-grained approach. So the IntServ that we are talking about, which we'll be looking at in detail now, is an example of this category. So we also have coarse-grained approaches where we provide quality of service to large classes of data or aggregated traffic. So the diffserv mechanism, it's called as differential services, in short it's called as diffserv, which is also widely used. So that is a coarse-grained approach mechanism, an example of coarse-grained approach mechanism. So we will look at that later. We will now be looking at the IntServ mechanism. So if you look at integrated services, it basically refers to a body of work that was produced sometime in 95-97 time frame. What this actually does is it specifies a number of service classes, okay, which are basically designed so that you can meet the needs of different application types, and also defines how the RSVP or the reservation protocol can be used to make reservations for these different service classes. That's the overall picture of what integrated services is expected to do. So we look at the details now. So in IntServ, a flow is the basic management unit. We said it's a fine-grained approach. So we provide quality of service guarantees per flow. So it's a per flow approach. So it supports accurate quality control, and the resource reservation that we require is dynamic, and all traffic control functions are embedded in one router or in each router to say. So all the routers in the network have to be IntServ aware in order to support integrated services. Okay. So let's look at the various components that we require for integrated services. So first thing we look at in terms of the components is what is the network promise? So what is the type of service model that we are talking about in integrated services? Second is the service interface, that is how does the application describe what it really wants. So it has to describe it to the network, and then the network and the application have to get into a contract, right? So how does it happen? Third is what kind of packet scheduling is done, that is how does the network meet the promises that it has made. And fourth is how do you establish the guarantee, that is how is the promise communicated to or from the network, one, and how is the admission of new applications controlled, right. So these are two things which will affect providing the guarantee, because if you already have enough resources that have been committed, then you may not be able to accommodate new applications. So how is it that you will control the admission so that you will be able to provide guarantees for all the flows that you are permitting into your network. So integrated services tries to answer all these questions. Okay. So we'll look at how each of these things is handled. So in terms of service models provided by IntServ, there are two service models. One is called as the guaranteed service and the control load service. Now these two are in addition to the best effort service that we normally talk about. Remember, our IPv4 is a best effort service. So the guaranteed service model and control load service model are the two models that we have. In guaranteed service model, you provide guaranteed bandwidth and there is a bound on the end-to-end delay. Control load, what it actually does is it kind of emulates a lightly noded network. We will look at some of the details of these. And then of course best effort is there, where there is no QoS that is provided. So if you look at the guaranteed service model, it basically targets hard real-time applications. So what this actually does is the user will specify the traffic characteristics and the service requirement, and whatever is specified by the user has to be guaranteed by the network, right? That is, he gives his requirement and you should be able to provide guarantee saying that yes, we will be able to meet that requirement. So what the network should guarantee is that the delay that's experienced by an application packet is less than the specified maximum value. So that is the guarantee that it gives. And obviously this requires admission control at each of the routers, because each of the routers must be able to provide this guarantee. Okay? And you can mathematically guarantee the bandwidth, delay and jitter. So that is how the guaranteed service model is worked out. So next we look at the control load model. In the control load model, what we are actually doing is you are emulating a lightly loaded network, even though the network as a whole may in fact be heavily loaded. Okay, so what do we mean by this? Now there are certain applications which can actually adapt to network conditions within a certain performance window. So you may have something which is, it's almost like saying this is something which is better than a best effort model. So normally without this kind of a service, you may just have to go in for a best effort service model, whereas here you are looking at something which is better than the best effort service model. So there may be some variations, but the application may be able to adapt to it. So that's the kind of service that you're expecting in the control load model. So here again the user will specify the traffic characteristics and bandwidth, and this will also require admission control at each of the routers. Okay. So next thing we talked about is the service interface. Okay, so what is the service interface? That how do you specify what you need to the network, right? So that is done by means of specifying what is called as a flow specification or a flow spec. So flow spec is the information that is that characterizes the traffic, and that is what has to be sent by the sender to the network. So this flow spec basically consists of two components. One is called the R spec and another called the T spec. So the R spec defines the QoS that is requested by the receiver. Okay, typically it is given in terms of the rate at which a receiver is willing to receive packets or can receive packets or can receive data. Okay. T spec specifies the traffic characteristics of a sender. That is, what is the rate at which the sender will be sending packets. This is normally specified in terms of either a token bucket or leaky bucket with a rate R and a buffer size B. So you are looking at saying that you may be sending bursts of packets which shall have to be accommodated, but otherwise you will get a rate of an average rate of about R. Okay, so T spec and R spec are two parameters which identify what the flow spec is. So this is how the traffic characteristics are specified to the network. And in addition to this, of course, for the signaling for the service interface, we also need to be able to specify these things. So we need a signaling protocol, and which is used to carry this R spec and T spec information, and RSVP happens to be the signaling protocol that's used with IntServ. Okay, third component that we need to look at is packet scheduling. Now for guaranteed service, we typically use a token bucket filter to characterize the traffic, which is described by rate R and bucket depth B. And in order to provide scheduling, weighted fair queuing is normally used at the routers, so that you can provide different weights for the different classes of traffic that you have. Okay. Next is call admission. Now call admission happens with the help of the RSVP protocol, because the RSVP is used to specify the reservation, and depending on the R spec and T spec that is carried in the reservation messages, the routers will admit the call or they will not admit the call. So when do they admit the call? So basically you have a request coming in which specifies the traffic, the T spec and the R spec, and what the routing element will do is it will consider its unreserved resources and the required resources. If it can meet the required resources without jeopardizing the existing calls, then it will reply saying it can admit the call, or it will say it cannot be satisfied, so the call cannot be admitted. So if the call cannot be admitted, that call cannot go on, cannot proceed. So this is the call admission process. So if you look at all these things together, there are two main things that we need to understand with respect to IntServ. One is flow spec, the other is the resource reservation protocol. Most of the other mechanisms are pretty much easy to understand, or we have already discussed things like packet scheduling earlier. So flow spec and RSVP are two new things that we need to understand with respect to the IntServ. So that's what we will now look at. Okay. So flow spec, as we said, has got two parts. One is the T spec, which is the traffic characteristic, which is the source's traffic characteristic, and R spec is, it describes the service which is requested from the network. Now R spec is normally service specific and kind of easy to describe, okay. And for instance, for control load service, there are really no parameters that are specified. But if it is guaranteed service, it's either a delay target or a delay bound that will be specified as the requirement. So that's how the R spec is specified. T spec is a little more detailed, is more involved. So if you look at T spec considerations, so what is it that we, T spec basically talks about the traffic specification, right, the traffic characteristics. So how do we actually characterize the traffic? So we need to pay attention to that, okay. So if you look at most applications, okay, the bandwidth is actually not a single number, it varies, right. For instance, if you take a video application, it will generate more bits per second when the scene is changing very rapidly, okay, than when it is still. So just knowing the long term average bandwidth is not enough, because suddenly you may get higher rates of bandwidth that is being used. So for instance, let us take an example. Suppose you have 10 flows which are arriving at a switch on separate ports, and they all leave on the same 10 megabit per second link. Okay. So if each flow is expected to send no more than 1 megabit per second, we have no problem. But if these are variable bit applications such as compressed video, what will happen? You will find that the rate will vary, right, across that whatever duration of time it is transmitting, there will be a variation in the rate. So which means it may go above 1 megabit per second too. So if there are many sources which are sending more than 1 megabit per second, so that the aggregate becomes more than 10 megabit per second, what will happen? Excess data that is sent will be queued, right, they will be sitting in the buffers, and the longer this condition persists, the longer the queue will get, so you will have more delays. So this is what will happen. So considering all these factors, what integrated services does is the T-spec specification is given in terms of a token bucket filter in order to take all these variations into account. So we have, remember we already looked at what a token bucket is. So the same token bucket idea is used here as a filter. So when we talk of a token bucket, there are two parameters which describe it, the token rate R and the bucket depth D, the bucket depth B. Okay. So how does a token bucket normally work? So to be able to send a byte, a token is needed. So to send a packet of length n, you will need n tokens. So let's assume that that's the understanding. So initially there are no tokens at all, and tokens are accumulated at a rate of R per second. Okay, R is the token rate. Now, since the bucket size is B, bucket depth is B, no more than B tokens can be accumulated. Okay. So let's take an example. So look at this. So assume that each flow can send data as individual bytes rather than as packets. Okay. To make it easy to understand, we will just take it as bytes rather than packets. So let's assume that flow A, right, this flow A is this, the one which is straight. Okay, it generates data at a steady rate of 1 megabyte per second. So you get 1 megabyte per second is generated. So you have a constant flow. Okay. So this now can be described by a token bucket filter with a rate which R equal to 1 megabyte per second, right, which means 1 megabyte of tokens will be generated per second, and a bucket depth of 1 byte. Remember, look at the bucket depth, just 1 byte. Why do we have it that way? So what it actually means is that it will receive tokens at a rate of 1 megabyte per second, but it cannot store more than one token. That is, it spends it immediately. So it's like a constant bit rate that we are looking at, right? So you will have the moment a token is generated, 1 byte will be sent out. So it will kind of get consumed as soon as it is generated. So you will have a constant flow. So this can be one particular type of traffic. So a source may be generating this kind of traffic. So it will be specified in this manner using a token bucket filter, these parameters for the token bucket filter. Now we have this other flow B. Okay, so let's look at how that is characterized. Now flow B, we can see, has a different characteristic. Okay, it will send at an average rate of 1 megabyte per second over the long term. Okay, but the way it works is, it does so by sending data at a rate of 0.5 megabyte per second for 2 seconds, and then at 2 megabyte per second for 1 second. So overall you can see how much that is sent. So 0.5 here plus 0.5 here, which is 1, plus another 2 megabyte here, which is, so 3. So 3 megabyte per second are sent over a time interval of 3 seconds, which averages out to 1 megabyte per second, right? So the average rate is 1 megabyte per second, but it's not sent as at a constant rate. Okay, so you can see that there is a burstiness in the traffic. So how do we characterize this kind of traffic? So this traffic now can be characterized using our R and B. So let's look at what we have to do over here. So you can say that since the average rate is 1 megabyte per second, the value R that we have, right, the long term average rate is 1 megabyte per second. So R will be 1 megabyte per second. But what about our depth B? Okay, now B cannot do with a 1 byte bucket depth, but it will require at least 1 megabyte of depth. Now why 1 megabyte of depth? So see that in 1 second it will generate 1 megabyte of data, plus to be able to send this 2 megabyte per second, it should have accumulated at least 1 megabyte worth of tokens, so that when it gets 2 megabytes to send, it will be able to send the accumulated 1 megabyte plus this additional 1 megabyte that is currently being generated. Okay. So you will need a bucket depth of at least 1 megabyte. So so now look at what will happen in this example. So here it could have sent it 1 megabyte, it only sent it 0.5 megabyte. So 0.5 megabyte worth of tokens will be there in the bucket. So similarly now during 1 to 2 time also, 1 to 2 seconds also, again another 0.5 megabyte of tokens would have got accumulated. So you have 1 megabyte of token accumulated, so that can be used up. So when you're in this time frame between 2 and 3, when I get 2 megabyte of data, I can send the 1 megabyte of data which is already accumulated, plus I will have another set of tokens being generated now, right? You will have 1 megabyte of token generated during this second. So that also can be sent out. So you will see that this kind of bursty traffic can be characterized using our token bucket filter, these parameters that we have. Okay. So this is essential to understand the specification in IntServ. Okay. Right. So this is what we are talking about here. So we have saved up this 1 megabyte of data which we are spending in the third second that we have. Okay. So if you look at the data plane in an IntServ router, right. So we've talked about how the specifications are specified. So in an IntServ router, what exactly will be there? If you look at that, so you will have a flow identifier, because you see that we have provided the reservations per flow. So there will be a flow identifier, and for each flow there will be a separate queue. So you will have these flow queues. Okay. At these flow queues you may have a polisher which is looking at the traffic profile that you have specified, and based on that sending it out onto a scheduler, and then the scheduler will send it out. Okay. So this is what you will have. And the flow identification will be done with the help of source IP, source port, destination IP, destination port, and the protocol ID, which is normally what we do for identification of flows. So this is what you will have in terms of the flow of packets in an IntServ router. So next let us look at the reservation protocol, which is used along with IntServ. So if you look at the reservation protocol, now there are very important considerations that we look at in terms of how this has been designed. So one of the primary considerations we have for designing our RSVP is that it should not detract from the robustness that we find in today's connectionless networks. Now given that we have connectionless networks, remember that because we expect a connectionless network, there is no state that is maintained in the network itself. So it is very much possible that routers crash and reboot, and for links to go up and down, whereas end-to-end connectivity is still maintained, right? End-to-end we still are able to transfer packets. We have our best effort service. So that's very important. So we should not lose this property of robustness that we get because of the connectionless approach. So we should not end up doing something which is very much connection oriented, which kind of jeopardizes this connectionless advantage that we have. Okay, and we do not want RSVP to replicate any routing functionality. Okay, and it should coexist with route changes. So if there are any changes in the route, so reservations should also have to change accordingly on the corresponding new route that is being used. So these are. So remember, what we are doing in reservations, you want to reserve resources along the path, right? So along the path, if the path itself changes, the route changes, you should be able to make the changes on the new path as well. So that's what we need to do. So considering all these things, what RSVP actually does is, it tries to maintain the robustness by using the idea of what is called as a soft state in the routers. Okay, so we will look at what we mean by soft state. Soft state essentially means that you do not actually kind of have fixed resources which have to be reserved using a connection setup and then teared down using explicit tear down has to be given and so on. It kind of gets done automatically. Okay, so that's the kind of soft state approach that is used. We will look at that in a little bit more detail. Okay, and RSVP is not a routing protocol, it only makes reservations. So RSVP is very clear about these goals that it sets for itself. Okay, second consideration that we have in RSVP is that it should support multicast. So now different receivers, when you look at a multicast scenario, you are looking about a single sender or even multiple senders could be there for the group, but at a time a single sender and multiple receivers. So when you have multiple receivers, different receivers could have different capabilities and they may want different quality of service, right? So we'll have to consider that also. And changes in group membership should not be expensive. You should be able to make changes to the group membership in an easy manner. And ideally, we would also like the reservations to be aggregate. That is, each receiver in the group should not have to reserve. If somebody has already made a reservation, I should be able to make use of that reservation for forwarding my traffic as well, for receiving my traffic as well. Okay, and you should be able to switch allocated resource to different senders. There are already allocated resource for a particular set of receivers from a sender. Now when another sender is sending data, I should still be able to use these resources that I have already reserved. So for these considerations, what RSVP does is, the reservations that it does, okay, are basically receiver initiated. Since you have many receivers and their capabilities vary, so depending on their capabilities, they make the reservations. This is very interesting aspect of the RSVP protocol. So this is opposed to what we normally do in terms of sender initiating the reservation. This is a receiver initiated reservation. Okay? And to support multicasting, it is basically sent on a multicast tree. So these are two things which are done in RSVP. Okay. So if you look at the role of RSVP as such, it basically rides on top of the unicast and multicast routing protocols, right? So it uses the unicast multicast protocols, kind of rides on top of them. And this RSVP mechanism has to be present at senders, receivers and at the routers. That is, all three of them participate in this RSVP mechanism. And it carries the resource requests all the way through the network, from the sender through the various routers to the receiver. Okay, and at each hop, it will consult the admission control mechanism and it will set up the reservation. And if there is a failure, that is, if not able to set up the reservation, it has to inform the sender and the receiver. Okay, so let's look at how RSVP basically operates. So the receiver needs to know the sender's T-spec. See, these are basic things that we need to understand about RSVP. So what are the things that are required? Receiver needs to know the sender's T-spec. That's the first thing. So now the receiver also needs to know the path that the packets will take from the sender to the receiver. Now why does that need to be known? So that it will be able to establish a resource reservation at each of those routers which are there on that path. Okay, so that's important. Now both these things, okay, in RSVP are conveyed by means of a special RSVP message called the path message, which is sent from the sender to the receiver. Now this message will contain the T-spec. So when this path message reaches the receiver, it's gone through all the routers, so all the routers know what is done, what is required, and is also received. It also reaches the receiver. Okay. Now each router looks at the path message as it goes by, and it figures out the reverse path that will be used to send reservations. Because it's going out on one path, we know that the reservation will come in the opposite direction. So that information it kind of captures and it stores. Okay. Now on receiving the path message, what the receiver will do is, it will now send a reservation back to the source, right, up the multicast tree. If there are multiple receivers, you know, they will be connected on a multicast tree to the source. So on that multicast tree towards the source, they will send this path, they will send a reserve message. Now this reserve message will consist of the sender's T-spec and R-spec, right, and will also, I mean, the sender's T-spec and also the R-spec, which is the requirement of the receiver. The R-spec is the one which specifies the requirement of the receiver. Okay, so it has both this information. So each router on the path now will look at this reservation request and will try to allocate the necessary resources which are required to satisfy it. If it can be made, that reservation request will be passed on to the next router. If it cannot be made, then an error message has to be sent back to the receiver who made the request. So if all goes well, right, your reserve message will go through the entire path and correct reservation will be installed at every router between the sender and the receiver. So as long as the receiver wants to maintain the reservation, to retain the reservation, it will keep sending this reserve message about once every 30 seconds. So you can see what is happening here. This is pointing to that soft state that we talked about. So what actually happens is that some state is maintained when a reservation is made, okay, but this information will be deleted on some kind of a timeout. Just for some time it will be maintained. If you do not get repeated reserve messages, that will be deleted. So which is why we call it as a soft state that we are talking about. Okay. So how exactly does, so we have talked about the overall process, we will look at some of the details of this. So the traffic in RSVP is defined in terms of three parameters, okay, session, filter specification and flow specification. So a session basically is defined by the two endpoints, that is, you have the destination IP address, whether it is unicast or multicast, and the destination port number. Filter spec gives you a type of filter that is used, so we will briefly look at that. And then flow spec we have already seen. Sender will give it as a T-spec, receiver gives it as a R-spec. Okay. So if you look at the RSVP messages, we already talked about something called a path message and a reserve message. In addition to this, we have something called a confirmation message. Now this confirmation message is generated only upon request, and it is unicast to the receiver whenever the RESV, the reserve message, reaches the node with established state. Okay. And then we have a tear down message which can be used to tear down the connection. We already made some reservation, you want to, once your data transfer is over, you will tear down that connection. Okay. And there is an error message that is used which will be generated if either the path message fails or if the RESV fails. Okay. So let's look at this path message. Okay. So we said that the path message will be sent periodically by the sender towards all destinations, and it will set up the path from the sender to each destination. So it contains the T-spec. Now remember, T-spec consists of maximum bandwidth, token bucket size and the maximum packet size. So this is what it will have. Okay. So RSVP path messages will be sent from the sender, okay, to all the receivers that are there. So you can see path messages going across down this tree. Okay. Now the reservation messages, the RESV messages, right? So they are sent by the receivers and they are sent upstream. So on the route which is set by the path messages. So if there are no senders, no reservation can be made. Okay. So we need to get a path message before sending a reservation message. And these messages are merged as the message proceeds upstream. Okay. And the messages are propagated upward, as we said, only if the reservation at that particular router is less than the requested QoS parameters. That is, if you are able to meet the reservation, you will pass it on. If you are not able to meet the reservation, you will not pass it on. So this kind of helps to conserve the resources in a multicast setting. So you can see this here. So reservation message, you have two reservations coming from these two nodes, which is combined here and sent to this node. Similarly, from here you have one reservation message coming, another coming here. Now from R1 you can see that there is only one single RESV message that is sent up. Okay. So you can see how the messages are combined. Okay. Okay. And there are two types of tear down that we talk about, a path tear which is initiated by the sender and a RESV tear which is initiated by the receiver. Right. These are basically to tear down the connection that you have already established. Now we talked about reservation styles. There are actually three different reservation styles that are supported in RSVP. It's called a wildcard or a no filter, which does not actually specify a particular sender for a particular group. Okay, says that any sender, so much of, I just want to reserve so much of resources for this. Another is a fixed filter where you actually specify explicitly for which sender how much of bandwidth has to be reserved. Okay, so it's kind of explicit reservation, so called fixed filter. And then you have dynamic filter where valid senders may be changed over time, so you would like things to change dynamically. So the fixed filter is suitable in situations like a video conference, dynamic filter for an audio conference and so on. So we'll just take a quick look at an example for each of these things. So let's say this is the scenario we have. We have two sources, S1, S2 and S3, right? I mean three sources connected to these two interfaces of this router A and B. Okay, A and B are the interfaces. Now at interfaces C and D, I have these receivers connected. Okay, C is connected to R1, D is connected to R2 and R3. Alright. So now let us say we want to take an example of this wildcard filter reservation. Okay, so what happens here? Now R1, R2 and R3, let us say they want to reserve resources of 4B, 3B and 2B respectively. Okay, so B is some given rate. Okay, so now this wants to make a reservation of 4B. Now these two together want a reservation of 2B and 3B respectively. So out of 2B and 3B, higher value is 3B, so you make one reservation for 3B. Okay, and towards both S1 and then to S2 and S3. Now you have not said for which source it is, right? For whichever be the source, I need to make a reservation of 4B. So up this path, right, you can see that both for S1 and on S2 and S3, on both these interfaces, a reservation of 4B is what is sent. Okay, so there may be other further routers down this path. Okay, so this 4B will be sent to each of them and they will make the reservation and they will keep sending it. So this is what happens in wildcard filter. So no specification of source, but we make the reservation. Next is a fixed filter reservation. So let's say R1 wants 4B for S1, 5B for S2. R2 wants 3B for S1, B for S3. R3 wants to reserve B for S1. So look at what happens here. So this specifies 4B, 5B, explicitly stated. So we have 4B, 5B specified here. Now this fellow wants 3B and B, right? Now R3 also wants B for S1, so which is kind of accommodated within this itself, right? So towards S1, now since this requires 4B and this requires 3B, you send out one message saying you require 4B here. And here between for S2 and S3, so S2 you require 5B, right? And for S3 you require B. So you send out a message saying S2 5B and S3B will be the explicit reservations that need to be made along this path. This is the fixed filter reservation. Dynamic filter reservation, we'll see how the information is shared. So let's say R1 wants to reserve B for S1 and S2 shared, okay, and similarly R2 wants to reserve 3B for S1 and S3 shared. R2 wants to reserve 2B for S2. Okay, so what happens in that case? So R1 wants to reserve for S1 and S2 together shared amount B. R2 and R3 put together, you can share the whole thing, right? For S1, S2 and R3, S3 together, they will need a bandwidth of 3B. So 3B and 2B put together, right? So you will require a bandwidth of 3B. So now what is sent up? S1 now requires, now if you compare these two put together, you require 3B for S1, that's what is sent over here. And for S2 and S3 also we require 3B, because here you require 3B, this fellow requires B, but here we require 3B, so this is what will be sent. So this is how the different filters can be specified. So and we said, we mentioned about soft state, which I'm reiterating the soft state in order to emphasize it's a very important aspect of the RSVP protocol. So soft state, the routers along the path would remove reservations based on timeout. So which is why path and reserve will have to be sent periodically, which is what will be used to keep the reservation alive. So basic advantage is that the network resource which is not reserved forever in case of node failure. So it will just quietly disappear, right? That's what will happen. Of course, the disadvantage is that we have a message overhead because you need to be periodically sending these messages. Okay. Now this RSVP can also be used for traffic engineering, so it can be used along with MPLS networks, which we find is one of the major uses of RSVP today. Though IntServ is not very popular, it's used along with MPLS networks for traffic engineering purposes. Okay. So to summarize, what we have looked at is this. With respect to IntServ, we've seen that IntServ is basically a fine-grained approach. We saw how FlowSpec is used to specify these traffic characteristics, and then we looked at how guaranteed service and control load services are done, and then we looked at the RSVP protocol. We looked at messages, filter specs, and soft state. So this is the overview on IntServ and RSVP. Thank you.